So we all know what an algorithm is. An algorithm is just a sequence of steps that are followed sequentially by a machine or some formal instrument like a computer, and that solves a problem. For example, sorting a file of a given size of 1,000 or 10,000, 10 million records, and they are indexed by one key, let's say the name of a person, and we want to order them in alphabetical order. Well, then we might come up with a method to do so, and actually there are more than one. But what makes an algorithm good? Well, first, we need to make sure that the algorithm does what it's supposed to do and that the algorithm terminates. These two facts are established through a mathematical proof, a reasoning that is totally logical and formal, and that leads us to the conclusion that the algorithm not only finishes on time, but it solves the problem that it's supposed to solve, including all cases. And up to here, the analysis is just reasoning and mathematical notation and mathematics, and all are in our favor and are the favorite tools to analyze an algorithm in those two aspects. But next, what we are interested in an algorithm is in the time it takes. How long does it take? How efficient is it? Because there are slower ways and faster ways to do things. Sometimes you want to make it slower. Sometimes you want things to be bigger. It depends on the nature of the problem and of our objectives. What do we want? So let's go back to the sorting problem. There are many sorting algorithms, and you may be aware of a few of them. For example, the insertion sort. Let's run the insertion sort in this application, which corresponds to the column titled insertion, and we will run the insertion sort algorithm using a random input. And you will see that the algorithm is indeed working and inserting the newer elements as it inspects all the files. It's inserting them on the right place. That's the way it's supposed to do it. And but there are many cases in which the input might be presented to the same algorithm, and that would affect their performance. For example, what happens when the input to insertion sort is nearly sorted? Well, we have a pretty quick behavior, and in fact, there is always a recommendation. I think there is a faster algorithm than insertion sort for an input that is nearly sorted. That means there's only a few elements that are out of place, and you need to put them back in order. And but that requires you to sort the whole file. But the algorithm that has the best time for this particular case is insertion sort. But look at what happens when we submit a reversed file, a file that is already sorted but in reversed order to insertion sort. Then indeed it has to visit all the elements and to insert them in their right place, but since the input is inverted, it's taking an enormous amount of time. Let's try another case, which is an interesting one, is when we have repeated values in the keys and the sort keys, but only a few values are allowed. Let's say if you have you may have 1,000 registers in a file, and only 4 names are involved. So many of those records will refer to the same person, so they have the same name. The same name will be repeated a number of times. But there are altogether only few names or few categories. So look at the behavior of insertion sort in that case. So let's now run the insertion sort for all cases and just look when does a particular input case finishes. Let's see what is the fastest case for insertion sort. By running it, we see that the nearly sorted input is always terminating first, and the reversed order is always the worst case for the insertion sort. So algorithms have their best case and their worst case, in which they can improve, and it all depends on the input. So let's say let's go to the other end and try to focus on quicksort, the naive quicksort, which is the next to last column, and let's find out which are the best and the worst cases for quicksort. As you see, almost all cases are done before the last one, when we have repeated keys. So we have a clear worst case for quicksort, which is, let's run it again to see if we observe this phenomenon again. And yes, in this case, always the input with repeated keys is the one that takes the longest for this particular method. But if we look what happens to quicksort when we have modified it with a median of 3 idea, then all of a sudden the worst case seems to be not so bad. In fact, it becomes the best case if we use, and the other cases are still very fast. Let's run all of them. So you can see in a comparison of all the sorting algorithms, we should prefer the quick 3 in most of the cases, but if we are lucky enough to have a nearly sorted algorithm, then we should prefer the insertion sort. So we are interested in the time. And why wouldn't we consider the average case running time for an algorithm? Well, because it is really hard we would have to model how the different inputs or different cases for inputs are occurring. So for our sorting algorithm, we might have, let's say, 4 cases. Case 1, it's totally sorted. Case 2, or case 2 is random. Case 3 would be the repeated values. Case 4 would be the reversed, or whatever way we order them. And then we need to find a distribution of these cases and say this occurs with this percent of the time, this occurs with this other percent of the time. In this case, is the more often. So, and how do we get that probability distribution? So in this case, we would have a probability in the y-axis. And how do we get these probabilities? Well, there are many ways we can do that. If we are lucky enough to have all the facts, we might try to do that mathematically, but usually we have to do that statistically, but through experiments. And we run the algorithm, and we run the algorithm again, we run the algorithm again, and under different circumstances, and we get an idea of this distribution. So whatever we do, getting the distribution for the average case is really hard, or impossible in many times. Okay. Now, also, even if the algorithm is tuned for a certain distribution, so let's say we found that this distribution and we are happy with it, it may perform poorly on other inputs. So we just may have a nice looking distribution, but maybe we are not including all the possible cases, and for the simple reason that there might be another case we haven't discovered yet, another input case we haven't discovered yet, and that can happen in reality. So in that case, can be really bad. So it would take a long time, and the probability and that may be occurring maybe a lot of times. That's what this would mean. Also, in the average case running time is not really telling us something related to the algorithm. It is more related to the nature of the input than to the nature of the algorithm. Okay, so let's start analyzing an algorithm. Let's say that we run an experiment with a given algorithm and we submit different kinds of inputs to the same algorithm with different sizes, and we get some results. This is actually something you would be doing in your project, although later on. So here you can see some experiments. For example, we have run for the algorithm 1,000 times, and the first experiment we got, we have run the algorithm with size 1,000, and in the first experiment we got 0.05 time units. For 2,000 we got this other time, for 3,000 we get 0.32, and so on. And as you can see, we repeat the values. The 1,000s again after we reach 5,000. We run it again with size 1,000, and now we get a different number. In the first case, we had a 1,000 size for the problem, giving us a time of 0.05. Whereas the second time, we got a time reading of 0.03, and the third time, here we run the algorithm also on 1,000 elements, and we have 0.01441, so we get different points, different times reported for files of the same size, or for input of the same size, but with different times taken because the input might be of a different nature. And so what we should do now, let's say that's from GNU plot. When we do that, we get the following output. In this plot, you can see that for size 1,000, all the times, we run it 4 times with each input size. And the points for the size 1,000 are all close together. The times we got for size 1,000 seem not to differ a lot between themselves. But when we increase the input size to 2,000, then we see 3 points, but there's actually 4 because we might have gotten the same value for 2 experiments. And they are a little scattered, more scattered than they were in the previous case. And for size 3,000, we get these values. 2 of them are clustered below the line, and 2 of them clustered above the line. And then for 4,000, we get an even more sparse case. But that's what happens in real time in algorithms. So we don't get exactly the same time whenever we run it. It depends on the input and also in some other factors, but the main factor is the input, not only the input size, but the nature and the modality of the input. So when an algorithm performs better or worse, it is usually determined by the kind of input it gets, not only by the size of the input, but of the kind of input it gets. So, as we learned from before, we may have different behaviors of a given algorithm for depending on the kind of input they get. And we have that there are best case inputs, or there is an average case or an average performance for average inputs, or there is always a worst case for a particular algorithm. And if that worst case is a common one, occurs very frequently, then that might be the most important case we should consider. Even if it's not the very frequent, it can happen. And if we take a conservative approach, we should focus on measuring the time or the performance of a given algorithm on its worst case. That is called worst case analysis. And so we are interested in the worst case running time because we want to obtain a bound on the largest possible running time. Okay, and we know that that running time will depend on the size of the input. Well, why are we so draconian? Why are we so hard and judge an algorithm's performance by its worst case? Because we're taking a conservative point. We just need to have an idea. If the algorithm runs fast, even if in its worst case, then it's a really good algorithm and we are safe. But if we were to take another idea, let's say the best case of an algorithm, we would be unaware and with our guards down, and there is the possibility of a worst case. And then if that worst case presents itself with some frequency, then the algorithm would give indeed a poor performance. So a conservative point of view is a safe one, and that's why we would like to take a conservative point of view and find an upper bound for the running time of an algorithm. And an upper bound would mean the algorithm cannot run worse than that, cannot have a worse behavior than the worst case analysis. So if we have an idea of the worst case behavior and we find a bound for the worst case running time, then we know that the algorithm, no matter what happens, will never do as bad as that upper bound, and that is safe. So we are interested in an upper bound for the largest possible running time of an algorithm. So we are not using the average case. We stick with the worst case running time analysis.